information. If I knew omega, I would know the future. All right? And as time goes on, as I get more and more data, I know what interval I'm in. So I pinpoint where omega is more and more and more. There's a really trivial example to see that. You know, I never know omega, but as time goes on, I know the nth bit, and so I know omega to better and better precision. It's a perfect example. In example 2, with t equals r, ft is just going to be the sigma algebra generated by a1 through an for all t. It didn't even occur to me to think about that until a moment ago. It just, because of the fact that I take t equals r, that means that I've been looking at this process since the beginning of time. At any time I could go back and compute the coefficients, and if I know all the coefficients, I know the future. so the information is just always the same. If r, even r plus, in a microsecond, you'd learn everything. So it's only if it was discrete time that this would, grow for a while, right? Okay, so this is when people talk about information in a stochastic setting, they mean filtrations. That it's synonymous almost. It's just all right. All right. So what do we do with this? So, God, it's almost the whole course. The thing is that once we get through this part of the course on stochastic processes, then when we get, all of the sort of statistics in the last third of the course is about looking at filtrations and state estimation, parameter estimation, things like that. So it's, we'll be practicing this until I say goodbye in April. All right. All right. All right. So, yeah. Okay, so before I get to the first application, I have to review something. And that's one regret I have, is I wish we'd spent a little more time reviewing conditional expectations. I think we will do a bit of that next week, but I put that back on you, to review that from noise 1. But so what do I mean by this? So, Shuang actually reviewed this, not in this abstract notation, not quite like this, but he reviewed what a conditional expectation was. So, I don't care about if the second moment doesn't exist. So let's just keep this definition. If you're in L2, that means that's the same as saying the second moment is finite, right? So it was defined to be a projection onto some subspace. But here there's no apparent subspace involved. Where's V? Well, V is equal to the set of all random variables Z in L2, square interval random variables, such that Z is a random variable for G. Right. Well, I'll make it. I'll fill it out. All right. So I've got a subspace which is the set of all square integrable, random variables with a second moment, such that this condition holds that z of omega less equal to c is in G for every c. All right. That just says that z is a random variable of this new probability space with the smallest sigma algebra G. All right. And we know that we get x hat here. The conditional expectation is an orthogonal projection. This error is orthogonal to any random variable here. Right? So this is a more abstract thing than was defined before. Before we just took G to be the sigma algebra generated by, say, T observations. But you can do this more generally. That's okay? Yeah. All right. So this allows us to talk about it as an uncountably infinite number of random variables. I mean, G could represent some crazy amount of information, It's not, there's nothing finite here anymore, like we defined before. But the definition is identical. You basically, there exists a x hat for which this error is orthogonal to any random variable in this class. And that is a definition of a conditional expectation under this assumption of square inability for x, which we might as well assume. Big deal. All right? Yep.
That big G, is that the same as the set of all functions of observations of y?
No, G's any sigma, no interpretation. Give me a sigma algebra, I've got a definition, it's no different than before.
It's different than the set of functions?
No, G is a sigma algebra. We know what that means. I gave examples of sigma algebras. No interpretation here. So I can give a general statement, and then I can go and give applications, and I will in a moment. All right, but G could be one of the FTs. That would be a typical example, is that G is one of the FTs over there. I'd like to compute the conditional mean of some random variable I haven't observed, given things I have observed. All right? It's a sigma algebra. All right? Like that. G could be FT. Did I understand the question, or?
It's as an object, right? It's just a set of functions.
No. G is not a set of functions.
G is a sigma algebra.
Sigma algebra is a sets of no. Sigma algebra are collections of sets. Nothing to do with functions. Oh, you're thinking about V. You're thinking about V. You think about V. V. The projection here. These are sets of random variables, which are functions of omega. So a Z here is a function of omega. Yeah. So if G was equal to the small sigma algebra generated by some observations, so now I know where you're coming from. If G was a small sigma algebra generated by some observations, I'm calling them y1 through yn because I think that's what the notation was in lecture 2, then it is true that any z here would be a function of those observations. That's what you're saying. So it's not the G, it's the V. So if G, again, if G is a sigma algebra generated by a finite number of random variables, then any z here can be written as a function of the observations. But that's too restrictive. We want to look at continuous time. This could be uncountable. I wouldn't even know how to talk about a function of a process. I'd have to be really careful what I mean by that. So yeah.
So V is basically the set of random variables which are defined on G.
Which are z.
V is a set of random variables.
Square integrable random variables, which the random variables on the smallest. You're absolutely right. Z is a random variable. You're absolutely. I'm just writing down what you said on omega G P. Exactly.
And that's the set.
V is a set of two criterions. It has to be a random variable in the smallest sigma algebra, and it has to be square integrable. Yeah. And then you have the projection theorem. All right, cool. Yeah, so that's it. Yeah. So I'm glad you stopped me there, because there's these two concepts. We have a sigma algebra, and then we have a family of random variables that are generated by them, or that are defined through them, right there. Cool, so we need that because I want to be able to define a few things. Looks likely. There it is. So there's a first definition of this. Yep.
You might have explained, but I just wanted to
Yeah.
confirm here.
Yeah.
What do we use by, instead of saying expected value of x given g, just expected value of x given z? Are we using
Where's Z? Where's Z? I don't see a Z.
the z?
No. The Z was one random variable. See, V is a collection of all random variables of this form. See, so in this special case is really cool, just in terms of thinking. You know, when G is something like this, I'm looking for a function of the data which best estimates X. It's a minimum mean square estimator, but the optimal nonlinear estimator. That's what's so cool. That's why I was joking that probabilists are brave to try to, but of course they can't compute anything, so they're brave without any reason. So we're looking for the best nonlinear estimator. So what we're doing here is we're just defining V with a set of all possible nonlinear estimators. But when G is abstract like this, it's hard to explain what that means. But again, with continuous time observations, you're stuck with this. And so we have this weird thing, is that I want to come up with the best estimator in the future, just at the mean, given observations up to time r. And my estimate is always the current value. Now, why is that important? There are books and books and books. So it just turns out that this captured the imagination of mathematicians who then spent their entire lives proving theorems about these things. And so if you can construct a martingale as part of your analysis of some algorithm, you can get all sorts. You can steal from all that literature, So, and I'll give examples in a minute. But it occurs to me. Again, one of the hammers in the stochastic optimization literature, like again at these machine learning conferences, is they construct a martingale. They use results from the literature, and from that they get bounds on rates of convergence for algorithms. And that is, you go through, you'll find just, I don't know, maybe 20% of the papers at NIPS, I don't know, will do that. And martingales are the only processes where you get such incredible bounds, like this. It's absolutely amazing. So it's a machine. So let's go through and try to look at some examples to understand this. So in this case, here T could be anything. It could be real numbers or integers, whatever. Oh, by the way, where did the word, nobody asked me what martingale comes from. I think if you're a horse person, you know, it's some sort of device that keeps a horse's head level or something. It's that's what I've heard. You know, maybe it's not used anymore, but it's. Anyway, random walk. So we're given. So we're given a collection of random variables, an initial condition x0, and a bunch of random variables I'll call delta k, and they're all independent, and you just sum them up. So you take, you define xk to be just x0 plus the sum, I should say n. Let's say xn, I want to keep the k there. So there we have a random walk, but what conditions will I need? So I assumed independence of all these guys. What more do I need to make sure this is a martingale? You know, my prediction of the future is just where I am right now. Zero mean. All right, and you know, and you can see it's a martingale really easily because if you look at, say, xn, oh, I guess I had a t and an r there. Okay, so now we're looking at discrete time. It's easy to use m and n instead of t and r. All right, but you can write xn as the first part plus the tail. And what's the first part? Just that. So xn is equal to xm plus some independent stuff. And so you take the conditional expectation both sides. Okay, so m is less than n, so this is the thing I have to check. When I take the conditional expectation, this whole thing, conditional expectation is a linear operation. And the conditional expectation of xm given fm is just xm. I'll put this on one side. Okay, so expectation is a linear operation. I've got a sum here. Take the conditional expectation. I can write it as a sum of conditional expectations. And then each one of these guys, delta k is independent of the past and zero mean. You can check that the orthogonality condition holds with just delta hat being 0. Okay, so a random walk with zero mean increments is a martingale. Okay, okay, but not conversely. You know, there's almost a converse. It's almost the same thing. And how would you think about that, you know? So put a big line here. Start over again. Xn's a martingale. And the question is, can I always come up with a representation like this? Well, if I could, what would the deltas be? So I've got an x0 here, plus a sum of deltas, and I get xn. Delta should be, yeah. Okay, so delta k equals the increments is the only choice, all right? And we do have xn equals xn minus 1 plus delta n. I mean, just look at it, you know. I mean, first of all, the telescoping, we do have that. And so from this property, from the Martingale property, we know that xm minus 1 All right, so the Martingale property tells us that this is true. That's the Martingale property, just, you know, just looking one step back. And then that, I just do the same thing as I did before, that's this. And so, let's do this again. So, I'll play the same game as before. Okay, so the Martingale property tells me once I make these definitions, I can take the conditional expectation here, and these guys cancel out. And so I get this property here. And you'll see this language almost as much as Martingale's. That a Martingale difference sequence is a sequence for which this holds. You know, so which the conditional expectation delta n given some filtration. It doesn't have to be, it doesn't matter what it comes from, but given some filtration, that's 0 for each n. All right. So that's not the same. That's a lot weaker than independent. You know, independent's a much stronger condition than this Martingale difference property. So it does mean independent under what condition? Going back to noise. I'll give you one more hint. If you basically, what's going to happen when I look at the expectation of the product of these guys for m less than n, assuming they're in L2 because I need this to exist. Yep.
Function of n.
Well, that function is going to be 0 because what I could do is I'm going to use this. What do you call it again? Yeah. So, I mean, I think you hear smoothing more often, but in the noise one, you hear tower is used. There's two equivalent, I mean, two names for this, that an expectation is an expectation of a conditional expectation. And given FM, I can take this outside, and then I get the expectation of delta n given FM, and that's 0. Okay, so it's uncorrelated. Okay, so that's an even weaker condition. So uncorrelated is much, 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 much weaker than a martingale difference sequence, which is much, 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 much weaker than an independent zero mean sequence, except if it is Gaussian. That's one reason we love Gaussian processes, you know, that everything is equivalent to everything, and they're very nice. All right. Okay. All right. Any questions? I'm going to leave martingales in a second. I just want to tell you, I said there are all these amazing results. I'll just explain what they are. I mean, there's a million. I mean, like I said, you can get books and books and books, volumes, all sorts of things. His two favorite results. So, oh. Okay, so we have a non-negative martingale, and we're looking at the max up till time n, okay? Now, you can imagine, given what I just said, being non-negative is a really strong condition, right? Because basically what I've said is that something like this always holds. I can get rid of this now. We always have this representation where this is a martingale difference sequence, you know? So it's going to take on positive and negative values. So the only way this can be non-negative is if we start off with a positive number. And also these guys somehow get smaller as time goes on. So the non-negativity is a strong condition, but you can find examples where this is really useful. And I want to balance something like the probability that this is greater or equal to C. And what would you do today, you know, based on what you know about this course so far? What? Well, yeah, I could use Trinov, I could use Markov, I could use Chebyshev, I could use all sorts of things. And there are versions for all of these things, actually. But the simplest is the sort of Markov thing. So yes, I could use Markov's inequality and stick an xn bar there. But then I'm saying that's something I don't understand at all. I mean, this is some complicated thing I don't understand. The magic is you can just stick an x0. And that's Dub's inequality. Just amazing, you know. So instead of what Markov's inequality, you'd have to put in the x bar n, you can actually just put in x0. Yeah, awesome. And I could put in any x because the means are all the same. Because of this property, the mean of x doesn't depend on time. Right? Take the mean of both sides. The Tower property again says the mean doesn't depend on time. And if I have second moments, I can compute the expectation of x bar n squared. And I think it's 4 times the second moment. I better check that. I think it's, yeah, is it 4? Yeah, 4 times the second moment of xn. All right, so, you know, looking at writing maximums comes up in detection problems. You know, you have some statistic and you're worried about you know, if it gets big, then it means it's danger, and you'd like to get a bound on that. And so this gives you a probability of a rare event. And this gives you something like a variance bound. Okay. In terms of things you maybe understand better, this thing is very exotic, the max, but these guys may be very elementary. All right. All right. So we're not going to do all of Brownian motion stochastic differential equations today. I'm sorry. But let's see how you go from a random walk to Brownian motion and how we get into this. All right, and then we'll quit, and we'll save the calculus for next time. And I should say, by the way, I'm following the book pretty carefully. So this is all in chapter 4 of the textbook. You'll find, maybe not this mention, but, let's see. Okay, so I want you to just get some intuition about what Brownian motion is. It's a building block. So I'm going to change the notation a bit. I've got my random walk sitting here with xn. I'm going to get rid of that and call it Sn. Okay, so before I said these delta k's were independent and zero mean, now I'm actually making them IID. And I'm just saying explicitly the variance is finite. And so there's a sigma squared, which doesn't depend on k because it's IID. The distributions don't depend on time. And the trick here is to define, this is a discrete time stochastic process. We define a continuous time stochastic process. So what I want to do is what am I doing here? To make sense of this, n here is an integer. So do you guys mind the floor notation? Wait, is that what I'm doing here? Yeah. Let me put it like that. So I want to define this for all time right away. So the floor, this means the integer part. So n times t is going to be some real number, and I throw away the decimal points. I just keep the integer part. All right. So that's the floor command in MATLAB. And so if t was actually k over n for some integer k, then there's no floor needed. This would just be k. So we're speeding up time, Basically, as thing gets larger and larger and larger, we're rushing through this random walk faster and faster, and we're scaling space by square root of n. Because if you make the sum go to a very large value, you're going to get this thing is going to become enormous, and so we need to somehow tame it. And so basically, it looks like this. Okay, so it's gonna be constant, and then it's gonna jump and be constant, and then jump and constant and jump. And basically that's S1, that's S2, that's S3, and so forth. All right, and we can go through and play around with this. Some observations. I mean, this was a martingale. What do you think about this stochastic process? You know, basically, given a time t, what's the conditional mean of the future? It's really no different than this guy. So it's a martingale as well. So it's a martingale, but this was a martingale in discrete time. Now this is continuous time. So this is a continuous time martingale. And we can compute its mean 0. And all sorts of other things as well. Let's kill all this.